Yeah, thanks for being here. Hope you enjoyed the conference so far. This talk is about real-time machine learning with Node.js. But before jumping into it, I would quickly reflect on my story, how I got involved in Node. So a couple of years ago, we were confronted with this task to collect internet data for some analysis. And so we scraped data of newspaper websites, scraped data of Twitter and other sources. And processing this data with Node turned out to be really great, right? Because you can easily collect the data, you can easily make post-GET requests, you can easily process HTML document and parse them using packages like Cheerio, say, and then being able to just save the data collected into a document store like MongoDB instead of having to deal with a relational database system where you don't really have a fixed schema at all. So that turned out to be immensely valuable. So we had all this data pipeline set up, and then the question became, okay, I asked myself now, turning to analyzing this type of data, do I really now need to go to Python or R, which would be like more common tools people would use to conduct such analyses? And I just want to avoid this context switch of having to use another language. And I don't see any reason why we can't do these types of tasks using JavaScript. All arguments you can make against JavaScript for numerical computing, for saying that it's single-threaded, or that you have memory limitations due to V8, all these arguments equally apply to, let's say, Python and R, and those are considered to be viable data science or computing platforms. So I think the one reason why Node has not really become really popular in that field is just that the libraries and the ecosystems are not there yet. So there are many people who innovate in that space, though. So we have many people who do interesting things. And myself, I teamed up with a data scientist, Eighth Nuins from Silicon Valley, and over the last 2 years, we have now kind of tried to build like a numerical computing, solid computing library called standardlib, and I will use this in some of the examples that I'm going to show. Now, turning our attention to machine learning. So what's really the goal that we try to address? Right, what can machine learning help us with? I would say, in general, it's about learning patterns from data. So we have a data set, which is probably pretty noisy, and we want to detect some regularities. We want to find out if we want to make some predictions, what variables drive other variables. And so machine learning really provides methods of finding the signal inside of all that noise, right? And this might be a very high-level description, but later on in a few minutes, we'll come back to machine learning and look at the different parts of it. And actually, the types of problems you can answer is pretty limited. So it's not that big of a field, actually, in some sense. But the first part of the title of this talk was real-time machine learning. So I would quickly talk about that. In the past, like in my field in statistics, people have always worked with static data sets, right? So you have a data set that was collected by humans, maybe in an experiment, and then you analyze this data set afterwards. But now in the internet age, right, we collect data on a continuous basis. If you're on a website, data comes in as a data stream. It does not come in one package, right? And so there are methods and algorithms which can account for that and which can actually be used and are better and more appropriate than some of the traditional methodology that people have used in statistics, let's say. And so here I would make this distinction between different types of training algorithms which will help you to build models. So we can think of what one can call a batch algorithm, where you basically build a model on your entire data set, and if you have new data, you would actually need to re-estimate everything. And on the other hand, there are what one could call incremental algorithms. Those are algorithms that where we build a model and we can actually update the model as we get new data. And in this talk, I will exclusively focus myself on methods like of this latter nature, okay? So now let's look at some very simple example. Here, it's just about estimating the sample mean in such a incremental fashion. So you could imagine that you have a website and you have customers coming to that site, and maybe it's an online shop and you're asking yourself how much are they going to spend on that page. In this case, a good estimate might be just the average, or maybe the median might be even better, if you don't have any other information, say, about that customer, right? So how could we do this? So here I first load some NPM modules. So the first one is a random number generator that we've written, and the second one is this module to estimate the mean incrementally. So why am I requiring here this random number generator and not just using math.random, right? We have that. I think there are two reasons for this. First one is that math.random obviously is depends on which browser you're using, what results you get back, and also it's not seedable, right? So you cannot get reproducible results using it. So that's why we decide to supply our own. And now how does this work here? So here it's pretty simple. We just we call this incremental mean function. We get an object back, which is now this accumulator, and then this will hold our current estimates, and then we can just update it as data comes in. So here we get some new data, numbers between 0 and 100, and then we update it. And if we want to get the current estimate back, we would just call the function without supplying an argument. Okay. So now prediction is an inherently difficult task. And this quote of Niels Bohr says that it's especially true if it's about the future, right? So why is that? It's because not necessarily the past is reflective of the future, right? It can be that things change, right? As we've seen in the financial crisis, everybody had these models, and then they suddenly broke down because maybe some underlying parameters in the systems that we've looked at change. So this is a big problem because almost all statistical machine learning methods have as their basic assumption basically that the data is independently and identically distributed, which means that data that comes in today should be come from the same distribution as the data that came to yesterday or whenever, right? So, but in reality, in practice, right, there are often violations of this. So you might have data which, for example, time series, which often is not IID, where you have trends, right? Things can change over time. So time series is non-stationary. So if you shift the distribution in time, you would get different properties. And so there are methods to specifically deal with this. But often one can also think about how can one transform one's data so that the IID assumption might make more sense. Yeah? But this is something which is really important to keep in mind, because otherwise it's easy to to build models which might be not really good in the long run. So here, for this case of where we might have such a non-stationary time series, I just have a quick example how we could use a moving average. So the moving average, right, we could take only a window when calculating the sample mean of, say, some n past observations and only use those, if we believe that only they are indicative of the current process. And for example, in our case with the online shop, it could be that during the holiday season, right, people spend more, so maybe we should focus our time window on that. Here we have an example where it's about the currently free memory in our system. So I now load this incremental moving mean module. It has the same API. I also use the native OS module. We again initialize this accumulator. This time we pass in the window size. Here I set 5, so I only use the last 5 observations always. And then let's say every second we get the currently available free memory, and we update the mean, and we could also get it out all the time. So how could this look like? Here we see it could look like something like this. So we get the red line would be actually, let's say, incoming data, and then the blue line would be the moving means, okay? So, and if we change the window size, you will see that, let's say, here I have 38 or something. Now it gets much smoother, right? We smooth out all these spikes and troughs here, and that can be really helpful because it helps you to get a better sense of what the trends, let's say, are. So if you do data visualization of time series, that can often be useful method, also using moving averages to better get a sense of what the underlying trends are. So now we have looked at 2 simple examples of how can we calculate the mean incrementally and a moving mean. There are lots of tools in machine learning, right? If we go to more advanced methods, you can, like you might have heard about, like random forests, support vector machines. Now people are doing deep learning, like non-parametric neural networks. And so it can be easy to miss the forest for the trees. So I won't focus now on the different methods first, but let's look at the types of problems that machine learning can answer, because those are usually broken into only three different types of problems, and those are all, I think, pretty easy to grasp. So the first problem is here on the left. That's like a regression. In regression, we're interested to explain like a numeric variable, for example, housing prices, right, or house prices, and those might be driven by the size of the house, right, or they are dependent on like how many rooms does it have, in what neighborhood is the house located, etc. And so here in this plot, in the left plot, we could imagine that the x-axis would be like an explanatory variable, and then we have on the y-axis some variable that we want to explain. And then regression boils kind of down to finding a curve which best explains these data points that we have there. Okay, so those are regression problems. The next type of problems are classification problems. There, we do have a categorical response. So we don't have a number that we want to predict, but we want to predict a group membership. So in this little plot there, for example, we have three groups, like the blue, the green, and the orange group here of data points. And we might see that on the y-axis, if we have lower values, right, it seems to indicate that we end up in the orange group, right? So you want to find, like, basically find decision boundaries which help you to discriminate between the different groups. And one typical application, or one potential application for this would be, for example, if you do optical character recognition, right? You have, like in the post office, people who have handwritten like letters, and you want to detect what letters do they actually refer to, right? So that would be a classification problem. And the final type of problem is what's called clustering, right? In a clustering problem, we also want to detect groups, or we want to find groups, but it's actually pretty different from classification, although it sounds similar, because in this case, we don't know what the groups are, okay? So we might just have these gray data points now, and we want to say, can we kind of separate these into meaningful groups? And here, maybe we could detect two groups, right? It might be like in the upper right and then the lower left corner. So, but it's not something we can as easily evaluate. And it's not and the methods which are used for clustering are actually very different compared to regression and classification methods. So the first two here are usually also called supervised methods, because they require that we know what the outcome is and that we have some data with the outcome. And whereas clustering is called an unsupervised learning method. And here an example would be maybe we want to we are a movie recommendation service, and we want to find good recommendations for other people. So we might want to find groups of our customers that share similar tastes, so that we can generate new movie recommendations for our users. Okay. So now I would like to go through some examples for these different types of methods before wrapping up. So first, let's consider a regression example. Recall in regression, we want to predict a response variable, a numeric response variable y, by a set of predictors x. Okay, and the example that we are looking at is, let's say we were interested in predicting the number of versions that a package on npm has. Okay, so how could we do this? Like these are all kind of toy examples. So, but what we first do is I'm loading this package stream module, which allows us to connect to the CouchDB changes in the npm registry. And so we will get those as a stream. And then I'm loading this online regression module, which basically allows us to incrementally compute like a regression. I create a model with some parameters, so I don't have time now to go into detail, but I will point you to some further resources also what those might mean, and also we have documentation on that too. And then here, now we listen to the changes. If we get these packages back, let's just create maybe like we extract the number of versions, and then I just thought, okay, maybe age could be a good predictor, right? So let's use the age of the package in years, so how old is the package, and use that as a predictor for our response. And so then we update the model using this update method there, where we pass in first the array of predictors and then as the outcome variable, right? Because in an array, because we might have multiple of them, right? So what do we get back here? So here in this case, you see data points coming in, and we update as each data point comes in this regression line, okay? And it seems to be positive, like there seems to be a positive correlation, although as you can see, there's quite a bit of variation, right? So we would need a lot more iterations before we see like convergence here. And why is that? It's also because many of the data points are actually in the lower left corner, right? So every data point which corresponds to a package that is quite old will have a high influence on where our line lies, okay? But what we can see is definitely that there seems to be a positive correlation here. And if we were to interpret this, it seems to be like if like a package that is a year older than another one, it's on average should be like have 2 more versions on NPM, okay? Like if this was the true value, which it probably isn't, but so that's kind of an example for a very simple regression problem, right? Now let's look at the classification example. Recall in classification, we are interested about predicting a categorical response variable, again using a set of predictors X. So here, what I thought might be of interest is, so let's first constrain ourselves to like the binary case. So we have only 2 groups. I was interested in what kind of packages do, say, React.js projects use, right? And let's look at what we are doing here. So again, I hook into the CouchDB stream of the NPM registry. We also load this classification module, which has a similar API to the regression module that we used before. So we again initialize it with some parameters. And then we listen to the changes here of the packages. And so we get back these package objects. And then first I create this response, whether the package uses React, so which I just let whether React appears in it somewhere. And so if so, I will just assign it a 1, and otherwise a -1, okay? And then I thought it might be interesting to see, so React packages, right? We usually have different bundlers that you might want to use, like you either use Webpack or Browserify, and we have different testing frameworks. So maybe it would be interesting to see what are the differences between, like, let's say, Jest, Tape, and Mocha. I mean, there are many other testing frameworks, so you could try out on your own. I just picked those 5 for no real reason. And then after doing this, what I'm going to do here is now we predict the outcome, so whether a package uses React or not, using the features that we have, basically these 5 developer dependencies. And then I also, so I first get a probability, and then if that probability is greater than 0.5, we just use the corresponding, we say it's a React package, and otherwise we say it's not. Now, and afterwards here, I update the model using the features and the actual response. And that's like one important thing to keep in mind, or if you're doing machine learning in some setting, right, that your data kind of becomes tainted if you already used it for training your model, right? Then it will not give an accurate reflection of how good your model will perform on unseen data. So in this case, that's why we first predict the observation before actually using it to update our model, because otherwise we will underestimate the error that we will incur when we use our model on unseen data points. So let's look at how this could look like. So here, we see these packages coming in, and they're green if we get them right and red if not. And here on the right now I have this, what's called a confusion matrix. So here basically, right, we have these points and these if we get everything right. And then in the upper right corner we would have things if we don't, right, we predict that it doesn't use React, but in reality it does, so that's a false or negative, right? They are here. And like the false positives would be in the lower left, where we say they use React, whereas in reality they don't. So let's speed this up a bit. Then here we have this bar chart here for Webpack, Browserify, Jest, Tape, Mocha. And it's pretty clear that Webpack seems to be pretty indicative of. So these are kind of importances of these variables. And we can see that Webpack is like definitely the most important. So, and I think that's like, would confirm maybe the prior intuition, because many people use Webpack to bundle their React packages compared to Browserify, because it you can also bundle CSS, etc., right, more easily, I think. And concerning that here the testing frameworks, it seems that both Jest and Tape might be a bit positive, might be indicative of a React package. Mocha not so much. I guess the reason is that Mocha is just really popular in general, and versus like Jest is developed by Facebook, so might be more exclusively used by people who create React projects. Okay, so that's just a second demonstration of how we can use the classification method, also to look at what variables drive some outcome. And now I just want to. Okay, so now let's look quickly. I don't have the time to give you an example here about clustering, but let's just remember what's clustering, right? If we want to group observations into meaningful clusters, so that objects that we assign to one group are more similar than to those that are assigned to the other groups, right? And there are many different methods that you might have come across. For example, like one of the most popular ones is k-means clustering, which is like really efficient and gives generally good results. There are also some more recent ones like density-based spatial clustering for applications with noise, like this dbScan, which is, I think, also growing more popular, and then some older methods like hierarchical clustering, or like a probabilistic method called the mixture of Gaussians. So you might want to read up on those if you're interested in like doing a clustering exercise. I do have some further resources for reading. So there are some free textbooks actually that I can recommend, written by some professors at Stanford. Tip Giovanni and Hasty and others. And the first one is an introduction to statistical learning, which is like a more hands-on book that teaches R though. So, but no reason to be afraid. So R is actually pretty similar. R is the statistical language that all statisticians use, but it's pretty similar to JavaScript in the sense that it also has like C-style syntax. It also has like functional roots, so you have first-class functions, etc. So they also have accompanying lecture notes, so those might be useful. I mean, there's the famous course by Andrew Ng of Coursera about machine learning. That might also be a good resource. And then there's this other textbook, which is a bit more technical, The Elements of Statistical Learning. This is also freely available online, and I can just recommend to check that out. And finally, here's also the link of our numerical computing library that we are still in the process of developing, so we only have a dev branch there. But if you're interested, feel free to have a look, and if you want to run some of those models on your own. And with that, I would like to thank you all for your attention, and yeah, hope you enjoy the rest of the conference. Thank you.
Thank you, Philipp.